Alright, I want to start a video series here on automating the CRISP-DM process. I like this version of it that Nick Hotz put together here from the Data Science Process Alliance only because it's colored. It's a version from the same Wikipedia one that a lot of us have used. But the idea is here that we're going to create a deployment of some sort of machine learning prediction by solving a business process, exploring the data, cleaning, preparing the data, making a prediction, evaluating the results, and then deploying it somehow. Well, I want to begin with this step right here of data understanding, assuming that we've got a business problem that we want to solve, or any type of data science problem we want to solve, and it's time to explore the data. Automating this process to the degree possible is your key value add as a data scientist. It's what you provide that makes you unique from others. And I think it's really important to build up a kind of a quiver of arrows, your arrows being the functions you create that allow you to automate your own process so that you can accomplish as much work as possible in a short amount of time and focus your time on what should take the most time, which is typically this data preparation stage. This data cleaning is unique to every data set and domain, problem domain that needs to be solved. And that's typically where it's an area where we can automate certain steps, but we can't necessarily automate the entire process. However, much of the rest of them can be completely automated. And I want to start this video right at the beginning with data understanding. So here's what we're going to do. I've got in my book here just a description of what automation is. So we have three pieces here of automating our data science process. Automated first means that it's going to reduce human effort and decision making through code. We're going to use things like loops and reusable code and functions to not have to rewrite steps for every feature and data set that comes along. Dynamic means that it's going to work regardless of what inputs are provided. If we provide 2 columns or 200 columns, it'll work the same. 2 rows or 2 million rows, it'll work the same. Or categorical data versus numeric data, it'll work the same, or it'll work properly regardless of what inputs are provided. Sorry, that's dynamic. Finally, error resistant means that it's going to be uninterrupted even when unexpected events occur in the data. And we'll talk about how each of these steps apply here. So, like I said, we're going to begin by automating univariate exploratory data analysis. So, in the EDA phase, or when we do exploratory data analyses, we're often creating both statistics and visualizations that help us understand the cleanliness of the data and whether it'll fit for certain types of modeling. And we'll divide that into, or I'll divide that into univariate exploratory EDA and bivariate EDA. Univariate meaning statistics and visualizations that apply to one feature or one column at a time. And I've got just a little chart here I've made of the most basic elements that we're going to want to record. So if we get a column that's numeric, there's a bunch of measures that we're going to calculate for that and a visualization that we're going to create, typically a histogram or a box plot. If it's categorical, we won't necessarily have all the same measures. Some of them will be the same, and we'll use a different type of chart, a counter frequency chart. So I've divided this up, the function I've created before, into 8 steps, beginning with defining the automation function. So let's go through each of these steps and create ourselves a cool function. So in my chapter, here's all the code I've created for that one, but I'm going to start over from scratch here. So I'm going to begin by making a univariate function. And if this is going to work and be automated for any data set, then I need to be able to pass in a data set at its highest level, which is typically going to be a pandas data frame. And because of the concept of encapsulation, meaning anything that I need to use for this function has to exist within this function and be blind to all variables or packages in memory outside of the function. So since I want to pass in a pandas data frame and use it inside the function here, I better go ahead and import pandas so that I can use it here. Now, this is a common mistake. Many people will make a function and not import it because they already imported it somewhere above in some other code. And it'll work fine here, but I want to put this function in an external file where I can call it and use it for any data set. In that case, the function will break if I don't have that package also imported inside the function. So I'm going to put that there. All right, I've defined my automation function, and I want it to return something back to the user. Now, I'm going to go make a new batch of a new code cell here. And I want to give you an idea of where I'm going with this. So I showed you before that I want to include all of these measures and these charts in a single function. You might already be aware of the pandas describe function, which gets us partway there. So let me pull in a data set, make one called, I'll use the classic insurance data set, pd.read CSV. I have that in my Google Drive. Let's go ahead and connect and get this brought in. Okay, you know what? In fact, I've already got a link to it right here further up in my document. I'll put a link to this data set in the description if you're watching this on YouTube, or in the book if you're a student. But this data set, actually, you know what? Here, I'll show it to you right here. It's available on Kaggle datasets. It's a classic that's been used many times to teach medical insurance costs with linear regression. This will work. Yep, this is the right one. That's the data right there. We've got information on insurance charges. Each row represents a person. And then we've got 6 other features about each person, and then how much they cost, I think, in insurance that year, maybe, or some time period. It doesn't tell us what the time period is. So if you want this data set, just come and find it here on Kaggle or in the description. So now that I've got that, I'm going to head back down and pull that in. Let you see what this looks like. PD. Oh, good. I pulled it here in my function, but I didn't pull it in out here. So I need to go ahead and add pandas. And there we go. Here's my data set. First 5 rows. All right. What I want is to create those univariate statistics for this. If I just use df.describe, which you may have seen or used before, you'll notice that I'll get some of them. Count, mean, standard deviation, min, interquartile range here, the max. There's a lot of others that are really crucial for me when I do exploratory data analysis. I need to understand things like the skewness. To a lesser degree, I care about kurtosis, but also total number of unique values, missing values, data type. And notice that I'm only getting these back for numeric features. Describe doesn't handle anything for categorical features, region, sex, smoker. So I'm making my own univariate function above here to do a better version of this for what I need in my own process to do EDA for the CRISP-DM process. So I'm going to make, first thing, well, actually, let me go step by step here. So we've defined our automation function. Next, my step 2 that I put was import any packages we need within that function. All right, so far I've just got pandas as PD. Later on, I'm going to be using some others. I'm just going to go ahead and import them now. I'm going to want Seaborn as SNS and matplotlib.pyplot as PLT. So I'm going to add my visualizations directly to this function. Now, this is just one version of this function. You might want to make your visualizations in a separate function. I did that in this particular chapter in the practice problems. For this video, I'm going to include it all together in one, though. So now that I've got my Python functions, remember at the beginning of this book, we learned the IPO, input processing output formula for writing code. Now that I have steps 1 and 2 down, I need to write the code to take data in, and then I'm going to create some sort of iteration that is going to perform the processing that I want, perform that processing, and then there'll be some decision criterion that I use to make this dynamic so that my code applies regardless of data type, and add all that processing and then output my results. So next step here, if it helps, let's go ahead and create our output data frame that we want to print out our results down here. Kind of like this describe function. I'm going to create that variable right up front as a data frame, but I'll call it an output df or df output, something to indicate this is what I'm going to send back to the user. So I'm assuming you understand the concept of functions already. That was covered in a prior chapter, so I'm not going to go into great detail, but hopefully you understand that a function needs to return a value, and this is the data frame that's going to be returned from the function. So I'm going to start by saying create a data frame, and I'm going to begin by putting in only those columns that apply to all variable types. So in this case, both numeric and categorical variables, I can calculate a count of the number of rows that are not blank or that have data. Mean doesn't apply to categorical, but there's some others. For example, let's do type for data type, count, missing, and unique. Those four will apply whether it's categorical or numeric. So let's go ahead and next, we've got the variables we need for processing. Well, at least we've got the output data frame we're going to create. Next step I put in here is define the iteration. So when a data frame comes in, I want this function to work whether there's 2 columns or 200 columns. That means I'm going to need a loop. And I'm going to go for call in df to go through every column in the data frame. Now, I could do something like mark my label from my features, but at this step, I don't really care about differentiating between feature and labels when I'm just looking at univariate statistics. So since I'm not looking at any bivariate relationship, I'm not calculating correlations between a label and a feature or a label in itself, I'm not going to worry about excluding any columns from the data frame. That's my point. I just want to go through each column one at a time, and I want to calculate each of these values. So now that I've got my iteration set up, and this will run as many times as needed regardless of the data frame that comes in, I'm going to now go back a step to step 3 and create a few more variables that I need for processing. So I'm going to make one called type, or I'm going to call it dtype. It doesn't have to be named the exact same thing here that I call it right there. This is just a column title. This is a variable name, and the only reason why I'm not calling it type is because notice that's a reserved word. It would work anyway, I'm sure, but I don't want to overload or overwrite type, so I'm going to call this one dtype. And I want this to be set to simply numeric or not new. Well, I'll make it the data type of the column that I'm currently looking at. So here's something that confuses a lot of people. Call, what does this represent? Well, in my iteration, call, well, let's say we don't know. Let's actually just print it out real quick. That'll help. Let's print out call. And so when I run this cell, that stores this function in memory. Notice I haven't called this function yet, though. All I did was store it in memory so that I can call it later. I can do it in this cell, or I can come and add a separate cell right here. Actually, rather than put that one there. Oh, I didn't mean to do that. Well, let me undo. Let's see. Undo, delete cell. There we go. Rather than print out df head, I'm going to call Univariate after I pull in the data set and pass in that data frame I just read in. So I created a variable here called df where I pulled in the insurance data set. I'm calling this function Univariate, which I created right here and stored in memory, and I'm passing in this data frame right here. Now this is important. The df we are passing in does not need to be named the same as the parameter needed for the function. In other words, I didn't have to call this df simply because I also called it df right here. This is a conceptual data frame right here. When I define the function, this data frame doesn't exist. It's just a concept. Down here is where I'm passing in the actual data that I just pulled in. So real data just got stored in this variable, is getting passed in right here. This, I could have called this just as easily purple monkey dishwater, and then I would have passed in purple monkey dishwater right there, and it would have renamed it to df as soon as I called this function right here, and it would have worked just the same inside of this function. So let me show you what I mean. If I run this, notice it just ran the function, and it went through every column that I passed in from this data frame and printed out the column names one at a time. It doesn't matter, again, that I name this df. It will, once again, work just the same. I can name this whatever I want. All right, so I've called the function, and I've printed out call. What type of data type is call? It is simply a string. If I were to print out call and then type call right next to it, call that function again, I get call each time through the loop. It prints out that name, and then the type of each one is nothing more than just a string data type. My point is, if I want to store the dtype I can't simply say call.type or put type around here, because every one of them is going to be a string. If I print out dtype, call is not the data type I'm interested in. What I want to know is, what is the data type of, let me print this out right here, df head. What is the data type of the data that's in each of those columns? So I want to go through and analyze each one of these and tell me that this is an integer, this is an object, this is a float, integer, Boolean. Well, I guess it's going to be an object because it's yes, no. So in order to get that, I can't just pass in call here. I have to pass in the data frame and then insert call as an index of that data frame. This is what returns the actual entire column of data right here. So by passing that in, I'm now looking at the entire type of that whole column. However, this type isn't the one I want. If I run this, it's going to come back and say, oh, that's a pandas series. A series is an individual column of a data frame. Oh yeah, if you remember back to the Univariate chapter earlier on in this book, you might remember that what we really need is dtype right here. Dtypes? No. I think it's just dtype. There we go. Yep, that's it. It wasn't pulling out, but it's a property, not a method or a function. It doesn't need the parentheses. So as a property, it says look at this entire column of data, and .dtype says look at the data inside the column. And now I'm printing out that dtype right here, and I'm getting, here's what we've got. Int 64, that's age. Object, that's sex. Float 64, BMI, and so forth. Okay, now that I have dtype, let's go ahead and calculate and store into a variable these others right here. So I'm going to make one called count. df, pass in the call once again, .count. I think this one is a method. We'll find out. If you ever forget, not a big deal. Just try it with parentheses. If you get an error, then you know it's a property and take them off. Missing, this one's df. And again, I'm assuming you've either watched a prior video or read a prior chapter and you get how to, or these methods or functions I'm using hopefully look familiar to you. You've seen them before. Whoops, I need .sum. Okay, and then unique we'll set to df call dot, I think it's n unique. There it is. Okay, so I'm just going to print those out and make sure that they're all working the way I want. Now, this might be a little bit overkill, but I always say when in doubt, print it out. That's how you know what's going on at any given time in your function. Always just print, print, print to make sure you understand every change along the way. So in this case, I've set these three columns. I've got dtype getting printed out first. Count 11338. I know that's right. Number missing, that should be 0 because there's only 1338 total rows. That means there's no missing data. Unique, total of 47 unique values for age. That sounds about right. Sex, there should only be 2. Correct. BMI, looks like there's quite a few. Children, 0 through 5, it looks like. That all looks correct to me. So I don't want it in this format though. I want to make a table that looks like this format. And I'm going to add a whole bunch more to it. But to be honest, I don't like having the columns above. I prefer to have the columns down the side and then each of these metrics across the top. Well, that's why I've created this blank output data frame right here, which we haven't used yet. So now that I have each of these values calculated, rather than print them out, I want to insert them as a row in this data frame. Well, I also don't want to click print on the data frame. That's okay. You might remember the way functions work is we always have a return statement through every critical path that comes out of the function. In this case, we just have one path at the end, and we're going to return output df. I'm going to go ahead and get rid of this df.head down here so that it doesn't block the output df that gets returned. If I run both of those, you'll see I still have my print command. It's still printing these out right here. But now it's also returning this blank output data frame that I made right here. And you can see those column names that we created right across the top there, and no rows because we haven't inserted any rows into this new data frame yet. But hopefully you understand the concept of a function. When I call a function, anything in the return statement comes back wherever this function is called. And even though I didn't click or I didn't add print around this, naturally it prints out the results down here since it's the last line in the code cell. So all I need to do is replace this line with a line that will insert these values into this data frame instead. All right, turns out that's not too hard. All we need to do is change this print command to an insert into the data frame, in particular the output data frame that we created for this reason. And we're going to use the .loc index property, which allows us to insert or update a row. And then I want to set that row equal to a list of these variables that we created right here. And the list here needs to match the columns that we created up here. So I'm putting in a data type, the count, missing, and unique. Now .loc, again, you might remember this lets us access a row based on the row index or the label. For example, in this df.describe, their index was the name of the metric that they wanted to include in the table. Other times you've seen here, let me print out the pandas data frame again. Other times you might notice that in this case it gave us an automatic row index 0, 1, 2, 3. That's what .loc is referring to. So rather than let it automatically create one, 0 through whatever like this one, I want to insert a name for each index. So to do that, I want it to be, you might remember I mentioned before, I like to flip the orientation to where the column names are down the rows and then the metrics are across the top. So where do I get the column name from? Hopefully you've realized or remember that's what col is for. Col was the name of the column we're on, but rather than keep it as a column name, I'm making it a row index down the side of my output data frame and then inserting those 4 values. So if I run these now, there we go. I get each of the column names. So the first time through the loop, let me start over here. I pull in a data set, has these columns across the top of that data set. I call the univariate function, passes in that data frame right here, creates the output data frame, loops through the input data frame, and then one at a time calculates these metrics. So the first time through, its call represents age. And then right here, I'm saying create a row with the index label of age, and then pass in these 4 values that were calculated right here. Sure enough, that matches up. Age is an int 64. That's what's calculated right there. Count, number missing, number of unique values. This is our table. We could, if we wanted to, formally create an index title for this one. For example, we could, I think if we just add right here index, index, is it call? No, just index equals, and we'll make one called feature. Oh no, sometimes it doesn't like it. I think it may want us to put it in brackets because you can have more than one. There we go. Oh, this one put it as a row. I think, is it supposed to be index call? No, we're going to do this a slightly different way. I'm going to add feature as a column right here, and then right afterwards I'm going to set it as an index. Output df.set index. Feature in place equals true. There we go. So it just gives the index a name feature. It wasn't particularly necessary. In fact, you're welcome to skip that if you want to. And it just marks that that's the feature name, and then this is that's the name of the index, and then these are our columns. Okay, so what we need to do next now is decide what other metrics we want to include besides these 4. These are the 4 that applied to everything. And actually I can think of one more. Mode applies to both numeric and categorical features. But then we need to calculate a bunch of metrics that only apply to numbers. And then maybe put in a blank or something for those features that are categorical. Now in order to do that, I need an if statement that lets me determine whether these need to be calculated, because as I go through the data frame, I only want to calculate these if that feature is numeric. Now I do have this dtype right here that tells me if it's int, object, float. However, I really don't care about the difference between an int or a float. They're both numeric. Basically, if it's numeric, I want to calculate all of these, mean through max, plus a few others. And if it's not, then I'll just put in a blank or a dash for those spots. So let's go through and add everything else we want. I'm going to first add mode right here. And in fact, let's make sure we add it up here as well, because that applies to both numeric and categorical. But then I'm going to put in the rest that only apply to numeric. So I'm going to start with min. Let's break this down into a couple lines. I'll do Q1, median, aka Q2, Q3, max. Then I'll do mean, standard deviation, skewness, kurtosis. I'm trying to think if I've forgotten any. I think that's good. At least I'll call that good for now. You can add anything else that you want. All right, so mode, again here, calculate metrics that apply to all dtypes. After this, I want to create an if statement to determine if it's numeric or not, and then calculate those inside that if statement for only those that are numeric. So what am I going to use? You got a lot of options. There's more than one way to do this. I like to use pd.api.types and use the isNumeric dtype function. And it wants us to pass into this a column of data. Once again, I can't put col because that's just the string name of the column. I need to put the entire df call in there. And that's going to return a true or a false. So if it's numeric, meaning if it's either int or float, it'll accept both of those. In that case, I'm going to calculate metrics that apply only to numeric features. Else, if it's not numeric, I'm going to do something else. And then I'm going to pass in a row. So the question is, there's more than one way to do this too. I think what I'll do is pass in the row in both flows of this if statement, but I'm going to pass them in differently. And I'll show you what I mean. First of all, let's finish out this mode option here. Call.mode, and actually mode returns a tuple of 2 values, and we only want the first value. That's the mode. So this one's a little bit different from the rest how it works. And mode, since that comes after unique, I'm going to go ahead and put this in both paths here, the same, since it's calculated before the if statement. But then I'm going to have my other metrics, like min equals df call.min. I think that's a function. And for this one, I'll pass in min. But for this path, if it's not numeric, if it's an object, like sex or smoker, then it's going to skip this code. It won't calculate it. It's going to go to the if, and it will only run this code, where it will insert all of those values, which were calculated before the if, so that's fine. But for min, since we didn't calculate min, I'm simply going to put in a dash. You could make it a blank like that, or you could put in a NA, or you could even, if you really wanted to, put in a pandas none object type. I think I like the way the dash looks the best, so I use that one. So the idea is now we just need to go through and calculate the rest of them. And I think for speed, I'm going to just do a bunch of copy pasting here. Q1, median, Q3, max, mean, standard, skew, curt. All right, Q1, Q2, nope, sorry, Q3 I mean. Quantile for Q1, add 0.25, median, quantile for Q3, put in 0.75. Thankfully, the pandas named all of these pretty obvious names. Okay, now that I've got them all calculated, let's just put in each of them here. They've got to be in the same order. I created the columns up above, so min Q1, curt. And then down below, this is going to break if I don't have a dash for every one of them down here when they're categorical features. So again, I've got to have a dash for min, Q1, median, Q3, max, mean, standard deviation, skewness, kurtosis. I think that should do it. Let's go ahead and, whoops, run this and see if that works now. All right. Okay. Here we go. We've got feature, age, looks like it's calculated all these right. The mode is 18, min of 18. Okay, that makes sense because we know age is a very skewed, positively skewed feature. Actually, not very positively skewed. I'm a little surprised the mode is 18 and the min is 18. That's really the most common value. Huh. Okay, well, anyway, Q1, 27, median 39, Q3, that looks right. So 64 is the oldest age, mean of 40. Looks like it's actually very normally distributed and not skewed. So then we get sex here, which is categorical. Looks like we have more men in the data set than women, only 2 values. And then I just get these dashes where these other values didn't apply and didn't get calculated. So we could have also done something like we could have only printed out this row once after the if block and then set all of these in the else equal to the dashes. That would have been fine. I mean, there's more than one way to make this work. But the key here is we've completed each of our steps of the automation function. It's automated because it applies to any data frame, whether it's got 7 columns or 50 columns, and I'll show you that in a second. I'll bring in another data set. It is dynamic because it works regardless of whether the data type is numeric or categorical, and it's error resistant because we only calculate the features that apply to numerics in the proper flow control so that it doesn't break if we get data types that come in different orders in the input data sets. It doesn't matter what order they come in or how many there are. So let's pull in a different data set and see this work just the same. Another one that I like to use is I've got this NBA salaries data set. Whoops. I think it's just called NBA salaries. You can grab any CSV you want and run this. Oh, I guess that's not NBA. Let me find it real quick. Make sure I've got that right. Collab notebooks. Data. Oh, lowercase. Okay. That's what makes it cool. We've got a single function. In this data set, I've got a bunch of NBA players. Their salary. What's our max salary? I'm kind of curious. 4.8 million. Anyway, their position. Looks like the most common one is shooting guard. Games played, games started, minutes played. Automatically calculates everything we need. Doesn't matter what data set we drop in there. So this one just overwrote that one above. All right, not bad. Now, this is pretty cool, but I want to add, whenever I do exploratory data analysis, I think it helps a lot to have not just these metrics, not just the statistics, but you need a visualization to go along with each of them because this doesn't tell us the whole story. For example, when I look at salary here, I can see that, actually I'm going to stick with NBA salaries. I can see that I have positive skewness that is beyond the acceptable boundaries. I'm going to arbitrarily say -1 to +1 is acceptable skewness, and this is too skewed because it's higher than 1. All right, by looking at that, it doesn't tell me the whole story. So I'll show you what I mean. I want to print out a histogram for every numeric feature, and then I want to print out a count plot for every categorical feature. That's typically what we'll make. If you remember in the very first chapter, when it comes to visualizations, those are the most common charts we'll make for those two data types. So let's go ahead and modify our function to also include images. I've already got the function built, the iteration built, and the if block built. I'm just going to add, after I insert a row into the data frame, I'm going to create a visualization. sns.histplot. Data equals df. X equals, this needs to be the column name that I'm currently on as I go through the loop. So just call. And then in order to, the way the Seaborn and Matplotlib work, I have to delete the image from memory after I print it out, or else it'll rewrite the next image in the loop. So I have to call plot.show in order for it to keep each of these images. So let's do the same thing down here. And if it's categorical, let's do a sns.countPlot. Same thing, data equals df. X will equal the column that we're currently on. Plot.show. I guess technically I could call plot.show just once after the loop and save myself a bit of time. That's up to you. You can put it in either one. I'll save myself one line of code because, see, it'll only go and do one of these each time through the loop. And so I only need to plot.show once after I've created the plot. So that saves me a little code. All right, let's go ahead and run this. All right, generating. There we go. Automatically creates a plot for each one. And now it's probably, there you go, calculating the table. So I've got my table at the end, and then it made me the appropriate plot, either a count plot or a histogram, depending on the data type. So when I'm going through a project and working on exploratory data analysis, here's an example of what I might use all of this information for. First of all, this looks like someone just stored that data frame with the row index in there from the data frame and didn't mean to. That I would just ignore that one. Player name. Well, I could go through and modify my count plot so that it prints out the player names vertically. So I can mess with the properties of these things right here. Yeah, I'm not going to worry about it right now. I'll allow you can go through and look up how to modify charts, and you can put the modifications you want to right here in these spots. But anyway, this is clearly a useless plot because player name has a unique value for every single row. And this table tells me that. If I go to the table, I see player name, 467 rows, 467 unique values. That tells me that's a useless feature. I would just drop that one from my data set as soon as I read it in. So I would do something like this. df.drop columns equals, I would put that unnamed 0 or whatever it was called right there. Player name, I won't worry about this right now. I'll leave that off for now. I would just go ahead and drop those before I run it. Just because that and this other player name, who cares about a count of 1 for every player name. But let me show you another one that's kind of more useful. Here we go, salary. Remember how I showed you that the skewness was a 1.8? I knew the stat told me that it was going to look like this. But what that stat didn't tell me is that I've actually got 3 groups of players here. Notice how there's a nice smooth curve from here down to here, and then I get a bump and another bump. Okay, that tells me when I get to the modeling phase, there's going to be some other factors at play that define why I've got a group of mid-range paid players and a group of high-end paid players. And that skewness score by itself didn't tell me the whole story here. So I need the visualization as well to kind of give me clues. Well, why do I even want the stat if the visualization tells me everything? Well, on the flip side, if I were to look at this, eyeballing it, that looks to me like I've got a skewness score of more like 2, 3, or 4. I'm surprised that it's only 1.8, honestly, just by looking at this. So really the visualization doesn't tell you all, and the stat doesn't tell you all. We need both of them. Here's another example with a categorical variable. So there's a rule. Well, no, let me back up. So this is the position. In this particular data set, I'm pretty sure Steph Curry is the highest paid player, and his position is a point guard / shooting guard. Well, look, I only have a total of 2, I think, in the whole data set who are point guard / shooting guards. if I run a predictive model to predict salary based on all these other features, I'll tell you right now that it's going to come back and say the number one thing you can do to get paid more money is to become a point guard / shooting guard, because I've only got 2 of them in the data set and one of them is the highest paid player. Does that sound accurate? No, not at all. That's a bias that happens because I don't have enough data for this category. So this visualization tells me I'm going to have to do some data cleaning. How should I clean it? Well, that's the other problem. There's no one standard solution to every domain. If this was a different feature, like maybe country, and I had some countries represented that were really low, I could bin all of those countries into one category called other. Well, that doesn't make sense in this case. Why would I group point guard shooting guards with shooting guard small forwards and all these others? A better solution might be to bin this one with one of the other existing categories. For example, since I've got PG-SG, and then I've got the reverse right here, SG-PG, I'm guessing that they labeled people that were dual position players with their most dominant position first and their secondary one next. In that case, how about we just clip off the dash and the secondary one, and I bin Steph Curry with the point guards, bin all of these with the small forwards, bin these with the shooting guards, bin these with the small forwards. That might be a better way to handle it with this data set. So that's the whole idea behind exploratory data analysis, at least with the univariate features, is I'm looking for clues about data cleaning steps that I'm going to take later. And now we have a way to automate it. All right, so one last thing. Now that we have a way to automate it, I want to show you a better way to use this. So what I want you to do is I want you to open up either Notepad or TextEdit or VS Code or something that you can create a new file in. And I'm going to bring VS Code here into my screen. Again, you don't have to use VS Code. You can use anything you want, as long as it will let you save and create a .py file. Sorry, my windows here are getting a little out of control. Okay, so I'm going to create a new file, Control N, and all I want to do is copy this function out of my notebook and put it into a separate file, and I'm going to save this file as something .py. Now I've already done this in a prior step, and I just named this, I'd suggest something like functions.py or something like that. Whatever you want to call it, it doesn't matter. But this file is essentially going to become a list of all of your favorite functions that automate steps for you, and you can separate them. I can start another function right here. They just need to have a line break between them and be nested at the proper level. I can make a bivariate one next. In fact, I'll probably do that one in my next video, and I'll save it right here for now. So this functions file, but don't leave that there. I don't want to have any errors in this for now. I just want to create this and save it somewhere where you can access it from your notebook. So in my case, I saved it and I uploaded it to Google Drive. And I have a bunch of these files here. Where did I put this one? I think right here. Yeah, here it is. I made one and I saved it into a folder on Collab where I can access it. So it's just got the function in there, Univariate. Once I have that, I'm going to import that file just the same way that I would import pandas as PD. It's basically going to become a library or a package that I can access from. Now, in order to access it, though, I need to not only find it in here. Let me go find it. Let's see. Right there. Okay, here's my functions file that I saved and put in Drive. I want to copy the path to that file, but not to the file itself. I only want to copy the path to the folder that the file is in. So mine is in this folder called M-Class Notebooks. Just find the folder that yours is in, and don't copy path from the file, copy path from the folder. Because what we need to do is we need to add a path to that file. Now, your environment path is an environmental variable that lets your compiler know where it can run code from. And if you're in Collab right now like me, they've got a path already set up. We just need to add the location of this folder to that path as another alternative place to import functions from. So to do that, we're going to import sys and then sys.path.append, and we're going to paste that path that we just copied. Again, not the path to the file, the path to the folder that the file's in. So once we've done this, we basically just told the environment that this is another location where we can import libraries from. Because right now, if without this line, it's only looking in the default Collab environment to import paths from. So now that we have it, I can simply say import functions as fun, or whatever you want to call it. Now notice I put the name of the file. I don't add the .py. So I do this without the .py. Also, it puts this squiggly line under it. Ignore that. Don't worry about it. It's simply, it hasn't run this line yet and it's not looking there for a path. Just, it'll work fine. Don't worry about that. So functions as fun. Also, you got to spell it. You got to capitalize it correctly. If I didn't capitalize the file, don't capitalize functions. Just keep it just like that. So now that I've got that imported, I can simply call, actually I'll do it down here. Let me run that. And down here, I'm going to call fun.univariate. And now it's referring to the function in this file. And I can run that. And I can run this again. Oh, here we go. Unnamed 0. I'm going to go ahead and drop these now. Make sure I spell that right. Unnamed 0, yep. And then player name. Got to make sure I spell those right. In place equals true. Drop those columns. There we go. Now it's running this function from this separate file. So this is how you build value in your own personal brand as a data scientist. Automate everything you do. If you're going to spend the time writing all that code to build a cool exploratory data analysis function, great. Make it fully automated, dynamic, and error resistant. And then, and I really did very little, by the way. I mean, I didn't add any try catch blocks or try except blocks. I did very little to make this error resistant. There's a lot more you could do to improve this function, and I'd encourage you to think through that. I have a lot more in my own personal functions that I won't show in these videos. That's how I add my value or build my brand, is I make these really cool automated functions that do most of the work for me so I don't have to replicate it every time I've got a new data set. And then I just pull in any data set I want, run it through those functions, and it speeds up my time quite a bit as a data scientist. All right, hopefully this was helpful to you. I'll proceed and make one for bivariate exploratory data analysis next.